Hello everybody, my name's Jeff Jenness and I'm the GIS analyst here at the Springs Stewardship Institute, and I'd like to discuss some strategies for choosing springs to survey. I'm not going to go into a whole statistical sampling design course in this short talk, but instead I'm going to just discuss some methods that we use to select springs to survey in a way that balances our limited resources with our general goal of selecting a good representative set of springs. Now, in some cases, of course, you just want to survey specific springs for whatever reason. Now, they might have characteristics that warrant regular surveys. They might have endangered species. They might have unique cultural values to local communities. In these cases, there really isn't any mystery or choice about what springs you're going to survey, and so that's a fairly common and reasonable scenario. So when we do have a choice, though, then we prefer to go with randomization. Now, randomization is one of the fundamental ideas of statistics, and as I'm sure you know, if you want to study a sample from a larger population and you hope what you learn from that sample will apply to the larger population, and your best bet is to randomly select your sample. If you want to draw conclusions about all springs on the landscape based on the springs that you survey, then you should randomly select your sample from that population of springs. So, for example, suppose we want to survey springs on the Coronado National Forest. There's a lot of springs in the area, and in this case we're just interested in those springs in the unique Sky Island mountain ranges of the Coronado Forest. So if we want the things that we learn from our sample to apply to all Coronado springs, then we want to select our springs to survey as randomly as possible. So in this case we'll plan on surveying all of these yellow springs on the map. Of course, and as I'm sure you're aware, pure randomness can lead you to miss areas. It's just the nature of randomness. And as it turns out, this particular selection of springs misses a couple of mountain ranges. So it's important for us to sample, or if it's important for us to sample in every mountain range, then this is a problem. So the solution would be to stratify the sample. This just means to split up our initial population of springs into smaller subsets, and then we just randomly select a specific number of springs from each subset. So if our goal is to select from each mountain range, then we could split the Coronado Springs into groups based on their range. Then we pick a random sample from each group separately. So this method guarantees that we sample from each mountain range and still gives us a reasonable amount of power to extrapolate what we learned to all springs in the Coronado. So random sampling is basic statistics and generally the most defensible method to select springs to survey. Now, random sampling isn't as easy to do as you'd think, though, at least not in ArcGIS, and surprisingly there aren't tools in ArcMap to randomly select existing objects on the landscape. There are ways to generate random surfaces and do various advanced statistical analysis that depends on randomization, but there's nothing to randomly select a set of springs. You can still do it, though. So we know of 3 methods that you can use to do it for yourself without relying on any existing tool. They all rely on writing code to various degrees, though. So the first method, so you can randomly select using custom ArcObjects code. You can do this either in the VBA window, or you can also create custom add-ons using Visual Basic or C++ with the .NET languages in Visual Studio. Now, VBA, by the way, stands for Visual Basic for Applications, and it's an optional installation with ArcMap. It's free. And you might have seen VBA in Microsoft Word or Excel or Access. It's also available in those products. And that's the method we use. It's got kind of a steep learning curve to get comfortable with ArcObjects. Once you've climbed the hill, you can really make ArcMap sing and dance. You can implement almost any idea you can imagine once you're this deep into the internal code. So this method is far and away the most versatile way to develop sophisticated stratification systems, and it runs really fast. But honestly, the learning curve is pretty intimidating. It's not something you'll pick up quickly. So at SSI, we're working on packaging some of our randomization functions into an ArcMap add-in that you can plug right into the software. We haven't finished it yet, but it's on the horizon. In the meantime, we are happy to help and offer advice if you want to try ArcObjects programming yourself. So moving on to the second method, you can use Python code. And in general, Esri is really pushing Python as their coding language of choice. It It doesn't give you near as much access into the ArcMap internal functions as ArcObjects code, but for simpler tasks, it'll get the job done. ArcMap comes with a Python code window ready to go, so you don't need any additional software. Now, Esri provides some sample randomization code and instructions at this link here in the video. This function will randomly select a specified number of rows or features from a table or feature class. Now, it's not a fast function for large data sets, though. I tested it in preparation for this workshop and thought it had frozen ArcMap for a while. But if you're comfortable with Python code, then you should be able to make this method work for you. Now, the third method is probably the easiest of the three, since it only requires 2 lines of code. You can do them right in the ArcMap field calculator window. It's based on a random number generator that ArcMap includes, and it's simple to implement. It takes a little creativity to turn these random numbers into a set of springs of survey, especially if you want to stratify your sample in any way, but it's doable. So this is all you have to do. You first create a new double precision attribute field, and you name it something like random number. Then in your field calculator window, you open up your code block section. You just add these 2 lines of code. And notice that the second line of code generates a random number and assigns it to this variable named myRandomNumber. The bottom of the field calculator window, you just plug in your variable myRandomNumber, hit OK, and it fills up your new attribute field with random numbers ranging between 0 and 1. Then, to pick some specified number of random locations, you just sort your table by your new random number field, and you select the first X number of records, and these will be a random selection of your springs. So, now randomization is definitely the gold standard for getting the best representative sample from your population, but it can have downsides when it meets the real world, and probably the most common problem is that it leads you to inefficiently allocate your resources. So if you're like most of us, you have a limited budget, time, and resources to complete the number of surveys you want to do, and some springs just take a lot more time and effort to survey than others. So for example, suppose we want to survey a bunch of springs here in the Chiricahuas. This map shows both the spring locations and the forest roads. Purely random sample, it could easily select these springs to survey, which are all in remote areas with a lot of difficult topography to traverse to reach them. It's better to spend our entire budget surveying these few remote springs, or is it better to survey a greater number of easily accessible springs? It's not really an easy answer to that question, unfortunately. You'll decide for yourself depending on the circumstances at the time. So at SSI, we often just don't have the resources to survey the number of springs we need to survey while using a purely random sample. And unfortunately, not all recorded springs actually have springs present, so there may have been mismapped decades ago. They may never have been there in the first place. So if there's no recorded surveys at a spring, then you're gambling your limited resources on whether it even exists. If the spring is extremely remote, then you're making a larger gamble. So, therefore, we often try to balance randomness with resource restrictions by focusing on springs that are within a few kilometers of known roads, and also on whether there is some visual evidence of spring and aerial imagery. Now, there's lots of reasonably good road layers for most areas, even really remote areas. And at worst case, we can fall back on the U.S. Census Tiger road files. The downside of Tiger is that occasionally you find roads that you were depending on the map had been reclaimed by nature decades ago, and we see that sometimes. There's a lot of good aerial imagery available, though. NAIP and the Esri imagery base map are both at 1 meter or better resolution, and sometimes you can use those to spot the springs. NAIP also includes an infrared band, so you can use the NDVI and NDWI equations to bring out your chlorophyll and water on the landscape. NDVI stands for Normalized Difference Vegetation Index, and NDWI is the same thing, but it's the Normalized Difference Water Index. Just uses the red band and either the infrared or green band to do a little math, and it ranks the landscape on chlorophyll and water. Pretty neat functions. So we can use these methods to generate a set of random candidate springs. Well, these methods generate the set of candidates, and then we can randomly select from that set of candidates. So, Given our map of springs and roads in the Chiricahuas, we might buffer the road by some distance, in this case 2 kilometers, and then we'll review these sites that are within this buffer in aerial imagery. Then we'll randomly select from our candidate springs, and this allows us to achieve the number of surveys we need to complete while still allowing for some randomness in our selection. Okay, now another topic, sometimes we want to target our survey effort at filling holes in the landscape. And in this case, we want to survey areas that have been relatively undersurveyed in the past. So density maps, or also known as heat maps, are a good way to do this. We start by selecting all the unsurveyed springs in the landscape, and then we run the Spatial Analyst kernel density tool to generate the density map. Visually, it helps us to quickly see regions in the landscape with relatively high densities of unsurveyed springs. Then we can take this a step further by generating contour lines, which let us find areas of equally high densities in the area. Then we pick a contour level and we just turn that into our sampling area. Then we'll randomly select springs in these target areas. Now, another method we use occasionally is to tessellate the landscape into equal-sized polygons, and then calculate the proportion of unsurveyed to surveyed springs in each of these little hexagons. This method quickly lets us identify undersurveyed areas, and we can randomly select the polygons, and then we randomly select the springs within each polygon. So there's a few tessellation tools that are available to you. First, ArcMap has one called the Generate Tessellation tool that makes squares, triangles, and hexagons. ArcMap also has a fishnet tool that creates squares and rectangles, and these are both tools available at any license level. If you're interested, there's a third-party extension that I wrote called Repeating Shapes. It creates all these same shapes. It also does dots and circles arranged in square and triangular arrays. It also lets you orient them at any angle, and it's a free extension if you want to download. And that's pretty much what I want to say. So next up is lunch, and then Andrea Hazelton will pick up the topic with survey types. So are there any questions?